The polarity of a covalent bond and the symmetry in the geometry of a molecule are used to determine if it's polar. So for example, carbon and hydrogen have a similar electronegativity, so the electrons are assumed to be shared equally in this covalent bond, and therefore this methane molecule is nonpolar. Now when there's a prominent difference in electronegativity, such as with carbon and fluorine, then the electrons spend more time around the fluorine, so you get a partial negative charge, and that leaves behind a region of partial positive charge around the carbon. So we draw the dipole moments from the positively charged region to the negatively charged region. So here we can see the dipole moments cancel each other out, and due to symmetry this molecule is nonpolar. Now generally where you have lone pairs of electrons, such as with the H2O molecule, the molecule is generally polar. So you can see here that the net dipole moment is going to point upwards, and I'll leave it for you to determine the polarity of these other molecules and post your answers or questions in the comments. The Lewis diagram of the acetone molecule is given below. Determine if the molecule is polar. So given that the carbon and hydrogen atoms in this bond have a similar electronegativity, so we assume that the electrons are shared equally in these bonds, and we treat them as nonpolar. Now for the carbon-oxygen bond, oxygen is more electronegative than carbon, so it has a region of negative partial charge, which leaves a region of positive partial charge around the carbon. And therefore drawing the dipole moment from the positive to the negatively charged region, the molecule has a net dipole moment, and therefore it's polar. Intermolecular forces are interactions between molecules in a covalently bonded structure, and these are broken apart when the structure changes phase, so for example from a liquid into a gas, whereas the interatomic forces remain intact in a phase change. And intermolecular forces are called van der Waals forces, or non-covalent interactions, as they're generally much weaker than forces in solid structures. So these are grouped into interactions between non-polar molecules, non-polar and polar molecules, polar and polar molecules, and ions and polar molecules. So they get stronger as we move from left to right. And hydrogen bonding is a special type of dipole-dipole interaction, which is stronger than regular dipole-dipole interactions. And we'll look at these interactions individually in more detail. London dispersion forces are weak interactions that occur between all covalently bonded molecules, but they're significant between large molecules. So even if you have a molecule that's nonpolar, the electron cloud might spend more time around one atom, and therefore you get temporary fluctuating dipoles due to the random motion of the electrons. So therefore larger molecules tend to have a larger polarizability, because you'd have the random motion of more electrons in those molecules. So substances comprising nonpolar molecules are generally liquids and gases at room temperature, and the boiling temperature generally increases with an increase in the size of the molecule. And if we look at pentane, so it's a liquid at room temperature, and the boiling temperature can be higher for a nonpolar molecule compared to a polar molecule. So for example, if you have octane, that has a boiling temperature of 125 degrees, compared to the polar molecule H2O, which has a boiling temperature of 100 degrees, because octane is much larger. Dipole-induced dipole interactions occur between a polar and non-polar molecule, and these forces are always attractive. So you can see that because H2O has dipole moments, when this non-polar oxygen molecule gets close to the hydrogen, it develops a partial negative charge, and therefore you get an interaction between the two molecules. So therefore the forces between these molecules are always attractive, and their strength increases with the magnitude of the dipole of the polar molecule, and also with the polarizability of the nonpolar molecule. So if you have a larger nonpolar molecule, you'll also have larger London dispersion forces that'll be more prominent between both molecules. Dipole-dipole interactions occur between polar molecules, and the strength of the interactions depends on the magnitude of the dipoles and also the relative orientation between the molecules. So the intermolecular interactions between polar molecules are typically stronger than between non-polar molecules that have a comparable size, because these interactions occur in addition to London dispersion forces between those molecules. Hydrogen bonding is the strongest type of dipole-dipole interaction, and this type of interaction occurs between molecules where you have hydrogen bonded to either a fluorine, an oxygen, or a nitrogen, because the difference in electronegativity between hydrogen and these three atoms is quite high. So here you can see the negative dipoles being attracted to the positive dipoles, and hydrogen bonding can occur between different molecules or a different part of the same molecule, as we'll see when we look at large biomolecules. Ion-dipole interactions are strong types of attractions between ions and polar molecules, and these are stronger than dipole-dipole forces, because you have a loss of an electron, which gives an atom a full charge, compared to dipole-dipole interactions, where the electrons spend more time around the particular atom, so you get a partial charge. The orientation of the molecule, so for example here, you can see that the repulsion from the positive dipole around the hydrogen is more significant than compared to this case over here, where the negative dipole is closest to the positively charged ion. And if the ion had a 2+ charge, where the ionic radius is smaller, that'll also result in a stronger ion-dipole interaction. In large biomolecules, you may get non-covalent interactions between different molecules or different parts of the same biomolecule. So for example, here we have glucose, which dissolves in water, and you'd have a strong dipole between the hydrogen and oxygen, and similarly another strong dipole over here. So these types of molecules can have ring structures, and that can result in interactions between different parts of this molecule. And this hydrogen molecule may induce a dipole on this non-polar CH covalent bond, and here you have a difference in electronegativity between the carbon and oxygen, so you'd get a negative dipole around the oxygen. And in this case here, you get a strong dipole and a weaker dipole between this carbon and oxygen, because the difference in electronegativity between carbon and oxygen is smaller, and you'll have a net downward dipole moment in this region of the molecule. And I'll leave it for you to identify the other dipoles in the molecule and think about their interactions. Many properties of liquids and solids can be determined by the strengths and types of the intermolecular forces. So a typical property is the vapor pressure, and for example, if we have a water liquid, the molecules are going to be moving around at different velocities, and if the molecule strikes the surface of the liquid at a high enough velocity, then it can escape the liquid. So effectively weaker intermolecular interactions result in more molecules escaping the liquid, and therefore a higher vapor pressure. Now in contrast, boiling requires heat being input into the system. So at the boiling point of water, all the intermolecular forces are going to get broken, and the liquid changes phase into a gas. So the boiling point of the substance depends on the strength of the intermolecular interactions. Now if we look at ice, and this changes phase by melting into water, well here the intermolecular forces get broken and reformed. So the melting point still correlates with the strength of the intermolecular forces. Given a table of properties for different molecules, and using your knowledge of intermolecular forces, why does H2O have a higher boiling point than hydrogen fluoride? Well, we can see that the molar masses are similar, and so are the dipole moments, but the boiling point of H2O is much higher. So we can't say that the dipole-dipole interaction or the London dispersion forces are responsible for the higher boiling point. And if we draw the molecules, we can see that both types of molecules are going to form hydrogen bonds, but what we can observe is that the water molecule has 3 atoms in which it can form hydrogen bonds, whereas the hydrogen fluoride molecule can form hydrogen bonds at 2 points. So given that 3 intermolecular forces have to be overcome, we can say that this is the reason why the boiling point of water is higher. Which intermolecular force causes acetic acid to have a higher vapor pressure than propanoic acid? So here we can see that the vapor pressure of acetic acid is higher, whereas both acids have similar dipole moments. And given that the molar mass of propanoic acid is greater than that of acetic acid, then we can attribute the higher vapor pressure due to London dispersion forces. And for clarity, we can draw these molecules, so just following CH3, and the carbons are bonded to each other, and then we have oxygen with another oxygen bonded to a hydrogen. And for propanoic acid, again we draw the carbons bonded to each other, and then we have H3 around one carbon, and then H2 around another, and then we have 2 oxygens and a hydrogen. So here we can see both acids can form hydrogen bonds with their molecules, and the propanoic acid molecule is larger. So the London dispersion forces are going to make it more polarizable. Let's rank hydrogen cyanide, H2O, and nitrogen gas in order of increasing vapor pressure. Well, given that N2 is a gas, well, vapor pressure applies to liquids, so we can ignore nitrogen gas. And if we draw these molecules, so hydrogen cyanide and H2O, well, H2O can form hydrogen bonds between its molecules, whereas hydrogen cyanide can form dipole-dipole interactions between its molecules, because there's a large difference in electronegativity between the hydrogen and nitrogen atom. And hydrogen bonding is stronger than normal dipole-dipole interactions, so therefore the vapor pressure of H2O is less than the vapor pressure of hydrogen cyanide. Which interaction is dominant between H2O and dissociated ions in an aqueous solution? Well, for example, when sodium chloride dissolves in water, you get sodium and chlorine ions surrounded by water molecules. So the negative dipole around oxygen gets attracted to the sodium, so you'll have something like this. And you'll have a similar arrangement for chlorine, except the positive dipoles around hydrogen will be facing the chlorine, and so on. So therefore the interactions between the ions and the water molecules are going to be ion-dipole interactions. If magnesium or calcium ions are placed in an aqueous solution, which has a stronger interaction with water molecules, and why? Well, the positively charged ions are going to be attracted to the negative dipoles around oxygen in the water molecules. And given that the atomic radius increases as we move down the periodic table, well, the nucleus of magnesium is going to be less shielded and it's going to be closer to the oxygen dipole. And because these cations have the same charge, then you're going to have a stronger ion-dipole interaction between the magnesium cations and the water molecules. Particle representations are useful for helping to visualize how intermolecular interactions can establish macroscopic properties. So for example, boiling point, melting point. So here is an example of H2O in the liquid phase, and we should pay attention to the difference in atomic radii of the molecules. So you can see that the oxygen atoms have a larger atomic radius than the hydrogen atoms, and the dipoles are oriented such that the negative dipoles around the oxygen face the positive dipoles around the hydrogen. And here we have hydrogen bonding between the molecules. Now in this example, we have sodium chloride dissolved in water. So because the sodium atom loses an electron, it loses a shell, and therefore has a smaller radius than the oxygen atom. And here we can see the negative dipoles around oxygen face the sodium cation. So here we have ion-dipole interactions. And have a go at making some similar observations for the next two examples, where we have hydrogen gas and sodium chloride in the solid phase. Ionic solids are tightly packed structures to minimize repulsions between oppositely charged ions. So here we can see, for example, the two-dimensional and three-dimensional arrangement of sodium chloride, which is a solid at room temperature. And here you have strong interactions between the oppositely charged ions, which gives ionic solids different properties like a low vapor pressure, a high boiling point, a high melting point, and so on. And ionic solids are also brittle, meaning that they fail catastrophically under certain loads. So for example, if you load this ionic structure as follows, then you get sliding of the layers relative to each other, and you may get two like charges as follows lining up. And due to the repulsion of like charges, once you reach the strength of the interaction, the solid will fail catastrophically. And ionic solids only conduct electricity in the liquid phase when the ions are mobile. So for example, when sodium chloride is dissolved in water. In covalent network solids, the atoms can be covalently bonded together in a 3D network, like diamond, where one carbon atom is bonded to four others in a tetrahedral arrangement. Or the solids can be multi-layered, such as with graphite. We have each layer being a sheet of graphene, consists of a bunch of covalently bonded carbon atoms, and then between the layers you have intermolecular forces. So covalent network solids can consist of one element, such as diamond, or multiple elements, such as silicon carbide, where one silicon is bonded to four carbons in a tetrahedral arrangement similar to diamond. So typically covalent network solids contain a carbon or a silicon because these have four valence electrons and can form a lot of covalent bonds. So due to the strong covalent interactions, these types of solids have high melting points, and they're rigid and hard because the covalent bond angles are fixed. And as you can imagine, the electrons are not free to move around, so that also makes them poor conductors. Molecular solids are made up of individual units of covalently bonded molecules that are attracted to each other through weak intermolecular forces. So here is an example being dry ice, which is carbon dioxide in a solid phase. So the individual CO2 molecules have linear geometry, so therefore the interactions between these nonpolar molecules are London dispersion forces. And this type of solid sublimates at a very low temperature. And as we know with ice, the individual molecules are polar, so therefore ice melts at a temperature of 0 degrees. And when this turns into a liquid, the intermolecular forces are created and destroyed, so therefore they're rearranged. And the density of ice is lower than the density of water. So in general, molecular solids have a low melting point due to the weak van der Waals forces between the molecules. They're poor conductors because the valence electrons are tightly held within the covalent bonds and the lone pairs around each molecule. Metallic solids, such as this magnesium bar, can be represented using a sea of electrons model. We have two valence electrons being delocalized from a magnesium atom, so given that the electrons are free, metals are good conductors of electricity and heat. So for example, if we attach this bar to a battery using a metal wire, then we create a potential difference, and these free electrons are going to be attracted to the positive terminal and flow through that wire. And metals are also good conductors of heat. So for example, if we apply a heat source, then the free electrons vibrate and they gain kinetic energy, and this energy is transferred between the free electrons. And metals are also malleable, and they're also ductile. And this is due to the ease in which the metal cores can rearrange their structure. Now in an interstitial alloy, such as steel, the interstitial atoms, being carbon, make the lattice more rigid. So typically for steel, there's 0.05% to 2% carbon. Large biomolecules can be formed in nature generally by living organisms or cells, or they can be synthesized. And in these molecules, non-covalent interactions can occur between different molecules or different regions of the same molecule. So for example, in this linear form of glucose, there's different polar covalent bonds. So dipoles cause instability of the molecule and lead to rotation. And this leads to the ring form of glucose, which is stable in an aqueous solution, compared to dry glucose over here. So this is called a monosaccharide, or a single molecule of sugar, and this monomer is bonded together to form a polysaccharide. And an example of a man-made polymer is polyethylene, where the monomer is ethylene. And polyethylene is formed catalytically at a certain temperature and pressure. So what you get is these repeating units of ethylene that form the molecular solid polyethylene. And the functionality and properties of these molecules are strongly dependent on the shape of the molecule, and this is largely dictated by the non-covalent interaction. Solids can be crystalline, where they are arranged in a repeating three-dimensional structure, or they can be amorphous, where the particles don't have a regular, orderly arrangement. And in both cases, the motion of the individual particles are limited. So here is an example of a crystalline solid with a body-centered cubic arrangement, and this is an allotrope of iron, which is called alpha iron. And an allotrope is really different structural modifications of an element, such as with diamond or graphite. And under normal solidification conditions, metals and ceramics have a crystalline arrangement. And the structure of a solid is influenced by interparticle interactions and the ability of the particles to pack together. So for example, in metals, where the core particles are arranged with free valence electrons, and there's no restriction on the number and position of the nearest neighbor atom, which leads to dense atomic packing. And another example is crystalline silica, and here is an example of amorphous silica, where the structure is not regular. Liquids take the shape of their container, and the constituent particles are in close contact with each other, and they move around and collide. And the arrangement and movement of the particles are influenced by the nature and strength of the intermolecular forces. So in this case, you have polar molecules, and an increase in temperature leads to the faster motion of the particle, as the particles gain kinetic energy. So due to this increase in energy, the intermolecular forces get rearranged. So the hydrogen bonds basically break and reattach. Now the solid and liquid phases of a particular substance have a similar molar volume, which is the molar mass on the density of the substance. So the molar mass of H2O in the liquid and solid phase is the same. And in the case of ice, when water freezes at 0 degrees, the particles have less energy to move around, and they become arranged in this open lattice structure. So therefore the density of ice is slightly lower than that of water, then the molar volume of ice is slightly higher than that of water. In the gas phase, the particles are in constant random motion, and they travel at different velocities. So here, for example, we have a diatomic gas, being hydrogen, and the frequencies of collision and average spacing between the gas particles depends on temperature, pressure, and the volume occupied by the gas. So for example, if the container is smaller, then the volume occupied by the gas decreases, and therefore the pressure increases, because the gas particles hit each other and the walls of the container more often. And when the particles interact with each other more often, that causes an increase in the average kinetic energy of the gas particles, and therefore an increase in temperature. And we'll make similar observations when we look at the ideal gas law. And because of the constant random motion of the particles, and the minimal effects of the forces between the particles, being weak van der Waals forces, then the gas doesn't have a definite volume or shape. So in other words, the volume occupied by the gas is going to keep changing. The macroscopic properties of an ideal gas can be related through the ideal gas law, which states that the pressure and volume of a gas is equal to the number of moles by the universal gas constant by the temperature. And we'll explain what an ideal gas is when we look at kinetic molecular theory. So one form of the universal gas constant can be written so liters atmospheres per mole Kelvin. And if we use this form, the macroscopic properties of the gas have the following units, where 1 mole of gas is equal to the following number of gas particles, and if the number of moles is constant, we have the pressure by the volume of the gas on the temperature is also constant. So if we have two states of the gas, we can write the following constant ratio. So for example, if the piston is pushed down in state 2, then the volume of the gas decreases, and then the particles of the gas bump into each other and the walls more often, so the pressure increases. And therefore, because the gas is going to have a higher average kinetic energy, then the temperature also increases. Dalton's law states that in a sample containing a mixture of ideal gases, then the pressure exerted by each component, being the partial pressure, is independent of the other components. So therefore the total pressure of the gas mixture is equal to the sum of the partial pressures. And the partial pressure of one of the gases is equal to the total pressure multiplied by the mole fraction. So here we have the mole fraction of gas A, where the mole fraction is the number of moles of one of the gases on the total number of moles in the mixture. Gay-Lussac's law is derived from the ideal gas law, for the special case where the volume is held constant and the number of moles of the gas is also constant. So if we divide through by V, we obtain the following expression, and if we're given this is a constant, the pressure is proportional to the temperature. So we can plot this linear relationship, and an example is if we apply a heat source, while the volume is held constant, then the molecules vibrate and bump into each other and the walls of the container more often, and therefore the pressure increases linearly with temperature. Boyle's law is also derived from the ideal gas law, for the special case where the temperature is constant and the number of moles of gas is also constant. So therefore the pressure by the volume of the gas is constant and the pressure is inversely proportional to the volume. So graphically this is a hyperbola, and we call this an isotherm. So for example, if we apply a heat source, to ensure the temperature of the gas is held constant, and we move this piston upwards, so therefore as the volume of the gas increases, the pressure of the gas decreases, because the particles bump into each other and the walls of the container less often. And conversely, if we push the piston downwards, thereby reducing the volume, the pressure of the gas increases. Charles' law is another special case of the ideal gas law, where the pressure is held constant and the number of moles of the gas is also constant. So therefore we can write the ideal gas law in this form, and therefore this expression is constant and the volume is proportional to the temperature, which is graphically represented by this linear relationship. So for example, if we apply a heat source to increase the temperature of the gas, so the particles bump into each other in a container more often, and if we leave this piston free to move up and down, then the gas effectively expands and the volume increases. So therefore the pressure can remain constant in this case. And really have a think about this. Two 2-liter containers of gas are separated by a pipe, and the left container has 12 grams of helium and the right container has 22 grams of carbon dioxide, and the stopcock is initially closed. Now assuming ideal gas behavior and a constant temperature, which gas exerts the highest pressure on the container? Well, given the ideal gas law, and the volume of each container is the same, while the temperature is constant, and you can find the number of moles of each gas, and therefore the gas with the higher number of moles exerts the higher pressure. If the stopcock is opened, find the total pressure exerted by the mixture of gases. Well, the total pressure, by Dalton's law, is equal to the sum of the pressures exerted by each individual gas, And you can find the individual pressures using the ideal gas law applied to each gas, and the temperature is given in degrees Celsius, which is 303 Kelvin, and you have the number of moles of each gas from part A, and the volume of gas is going to be 4 liters, with the stopcock removed. A mixture of helium and argon gas is confined in a 1 liter container at a temperature of 250 Kelvin. Now if the total pressure is 3 atmospheres, and the partial pressure of argon gas is 1520 millimeters of mercury, determine the pressure of helium in atmospheres. We're using Dalton's law, so we're given the total pressure and the partial pressure of argon, which you can convert to atmospheres, and solve for the partial pressure of helium. Now find the number of moles of both gases, so we can do that by applying the ideal gas law to each individual gas. So therefore you can solve for the number of moles of each gas. And if the volume is increased to 2 liters, what's the new pressure of argon gas? Well, in this case, using the ideal gas law, where the volume of the container is constant, and so is the temperature, so therefore the pressure by the volume is constant. So given the partial pressure of argon gas from part A, we can solve for the new pressure. The kinetic molecular theory, which is what the ideal gas law is based on, relates the macroscopic properties to the motion of the particles in the gas. And the key assumptions of the theory are that the particles of the gas are in continuous random motion, the collisions between the particles and the walls of the container are elastic, so there's no dissipation or losses in the collision. And the volume of gas particles is negligible compared to the volume of the container. There's no attractive forces between the particles, so under certain conditions the intermolecular forces are negligible. Now the average kinetic energy of a single gas or a gas mixture is proportional to the temperature, which is the absolute temperature in Kelvin. And basically for a mixture of gases at a given temperature, the entire mixture has the same average kinetic energy. Now using this equation, the average kinetic energy of a particle can be related to its average velocity, and the kinetic energy is in joules. The Maxwell-Boltzmann distribution gives a graphical representation of the distribution of velocities of gas particles at different temperatures, or a mixture of gases at the same temperature. And in both cases, the average kinetic energy is proportional to the absolute temperature in Kelvin, and that's from kinetic molecular theory. Now in the distributions on the left, we have the same gas at different temperatures, and the average kinetic energy can be written as 1/2 by the mass by the average speed squared, where m is the mass of a gas particle. So in this case, because the temperature is increasing, the average kinetic energy is increasing, and given we're looking at the same gas, the average speed of the gas particles is going to increase. Now in the second distribution, the temperature of the mixture of gases is the same, so therefore for the gases in the mixture with a higher mass, they must have a lower average velocity, because given that the temperature is constant, then the average kinetic energy of the gases in the mixture is the same. A mixture of helium and argon gas is confined in a 1 liter container at a temperature of 250 Kelvin. Which gas molecules have a greater distribution of velocities and why? Well, here we have two monatomic gases, being helium and argon, so given the mass of the helium atom is greater than that of argon, then the distribution of velocities of the argon gas particles looks something like this, and for helium they'd look something like this. So recall that the average kinetic energy of the gas is proportional to the temperature, and it can be written in terms of the mass of a gas particle and the average velocity of the gas. So therefore the average velocity of the argon gas particles is going to be smaller than the average velocity of the helium gas particles, given that both gases in a mixture have the same average kinetic energy, as the mass of the argon particles is larger than that of helium, and therefore helium has a wider distribution of gas particle velocity. Recall that the ideal gas law was for an ideal situation where the gas particles were spread out, moving at random velocities, and the volume of the gas particle is negligible compared to the volume of the gas. So an example of an ideal condition where the molecules fly around fast enough so the intermolecular forces don't have much influence on the behavior of the gas. So if we look at scenario 1 where we compress the piston such that the volume of the gas gets smaller, then the volume of the gas particles is no longer negligible compared to the volume of the gas. So given that the ideal gas law assumes that the gas particle is a point, and therefore the pressure of the real gas is greater than that of the ideal gas. Now the other situation is where you have a low temperature, so the gas particles travel at lower velocities, and the intermolecular forces become significant, which is near condensation conditions, where the gas transitions from a gas to a liquid, then droplets are formed due to the significance of the intermolecular forces, and therefore the gas particles bump into each other in the walls of the container less often. At 400 Kelvin, the pressure of octane is measured and found to be lower than the pressure predicted by the ideal gas law. Is this related to the invalid assumption of volume or temperature? Well, given that the real pressure is less than the ideal pressure, then this can't be due to the invalid volume assumption, because the volume of a real gas particle is greater than the volume of an ideal gas particle, which is treated as a point, and this would result in a higher pressure of the real gas compared to the ideal gas. So the answer is due to the invalid assumption of temperature. And just to give you some perspective, 400 Kelvin is around 127 degrees Celsius, and this is near the boiling point of octane. So therefore the deviation from ideal conditions due to temperature means that the gas is near condensation conditions. Under the following conditions, the real pressure and temperature of argon gas are measured as follows. Now, under which condition is argon most likely to deviate from the ideal gas law? Well, for a lower temperature, the particles are going to be traveling at lower velocities, so the intermolecular forces become significant. And for a higher pressure, the gas particles are going to be more clumped up together, and therefore the volume of the gas particles causes deviation from ideal conditions. So for case B, the pressure is the highest and the temperature is the lowest, so this is the case that's likely to cause the most deviation from ideal conditions. Octane is more polarizable than water vapor, which is H2O in the gas phase. Which substance is then most likely to deviate from an ideal gas, and why? Well, for octane, the intermolecular forces between the molecules are London dispersion forces, as the molecule is nonpolar. And between H2O molecules, you have hydrogen bonding, which is a special type of dipole-dipole interaction. So given that octane is more polarizable, given that the molecules are significantly larger than H2O molecules, then the intermolecular forces between the octane molecules are going to be more significant, and therefore octane is most likely to deviate from an ideal gas. Solutions are also referred to as homogeneous mixtures, where the macroscopic properties are uniform and do not vary throughout the sample. So here you have an example being brass, which is a substitutional alloy, and similarly you have steel, which is an interstitial alloy. Now an example of a homogeneous liquid is sodium chloride dissolved in water, and a homogeneous gas is air, which comprises percentages of the following elements. Now in heterogeneous mixtures, the macroscopic properties depend on the location in the mixture, and these can also be multiphase. So for example, ice floats on top of water because ice has a lower density, and here you have concrete, which is comprised of cement powder and rock or aggregate mixed with water to form a paste, which hardens into a solid block. And oil floating on top of water is an example of a heterogeneous liquid, and fog is an example of a heterogeneous gas, where air and water droplets are distributed non-uniformly in the atmosphere. The composition of a solution can be expressed in numerous ways, but the most common method used in a laboratory is molarity, or the molar concentration of a solution, which is the number of moles of the solute on the liters of the solution. So the solute is the substance that dissolves in a solvent. So for example, sodium chloride in the solid phase dissolves in water, which is H2O in the liquid phase. A solution consists of 3.2 grams of sodium chloride dissolved in 350 ml of water. What is the molarity of the solution? The molarity, being the molar concentration, is the number of moles of solute on a number of liters of the solution. So the solute here is sodium chloride, which we can convert from grams to moles by dividing by the molar mass of sodium chloride, which we can obtain from the periodic table, which gives the following number of moles over 0.35 liters, which is 0.16 moles per liter, or molar. And here we use two significant figures as per the least number of significant figures in the problem. A 2 gram sample of calcium chloride with the following molar mass is dissolved in water to produce 350 ml of solution. Calculate the concentration of chlorine anions in the solution. Well, the molar concentration of chlorine is the number of moles of chlorine anions on the liters of the solution. Now the number of moles of calcium chloride can be obtained by dividing the mass by the molar mass. And for every mole of calcium chloride, there's 2 moles of chlorine. So when this dissociates in water, you get 2 chlorine anions per calcium cation. So therefore the number of moles of chlorine can be obtained as follows, which gives the following result. And then dividing by the liters of solution and using the least number of significant figures in the problem, being 2, we obtain 0.1 molar. A solution consists of 3 grams of potassium permanganate, and this is dissolved in water to form a 100 ml solution. Now 40 ml of this solution is poured in another flask and diluted with water until the volume of the new solution is 200 ml. What is the molar concentration of the new solution? Well, the molarity of the first solution is the number of moles of potassium permanganate on the liters of solution. And we can obtain the number of moles by dividing the mass on the molar mass. And dividing by the number of liters of the first solution, we can obtain the molarity of the first solution. Now given that 40 ml was poured in the other flask, we need to obtain a number of moles in the new flask. So to do that, we can use the molarity, and that's equal to our new number of moles on the liters of solution that was poured in the other flask. And now we can obtain a molar concentration of our new solution using the least number of significant figures given in the problem, which is 1. Particular representations can be used to communicate the structure and properties of solutions. So for example, when an ionic compound, sodium chloride, dissolves in water, it dissociates into a 1-to-1 ratio of sodium cations to chlorine anion. So because sodium is an alkali metal and chlorine is in the halogen group, these each carry a charge to make this ionic compound electrically neutral. And here we can also observe that the negative dipoles around oxygen face the sodium cations, and the relative sizes of the ions and the atoms in the H2O molecule are consistent with the periodic table trends for the ionic and atomic radii. Now in the second example, chlorine is a halogen and magnesium is an alkaline earth metal, so therefore when dissolved in water, this electrically neutral ionic compound dissociates in a 1-to-2 ratio, and assuming the number of moles is the same in both solutions, then the magnesium chloride solution is a better conductor of electricity. The components of a liquid solution cannot be separated using filtration, but they can be separated using chromatography, which takes advantage of the differences in intermolecular interactions of the components of the substance. So in paper chromatography, you have a solvent and a paper with the substance that we're going to separate, which is the stationary phase. So for example, there's a black ink dot that's composed of a mixture of several covalent substances, and the paper is dabbed in water with the substance slightly above the water, and the solvent travels up the paper via capillary action. And as the solvent front moves upwards, the separated substances appear. So if the solvent is polar, like water, then the most polar component will travel the furthest, being the green component here. And this solution comprising the different components of the substance is the mobile phase. And defining the retention or retardation factor, then the most polar substance has the higher retention factor, because the solvent is polar in this case. Thin layer chromatography is used to separate the components of a solution, and it's similar to paper chromatography, except here you have a thin inert plate, for example glass, and that's coated with silica gel, which is a thin porous and polar coating. And this is the stationary phase. And the stationary phase enables the solvent to move through it against gravity using capillary pressure. Now this plate is placed in a closed chamber to keep the experiment stable by preventing evaporation of the solvent and so on. And the plate with the analyte on it is dabbed in the solvent, and the solvent front moves up the stationary phase and the analyte gets separated. And this solution with the separated components is the mobile phase. So in this case the red component is the most polar because it's attracted most to the polar stationary phase. And again, using the retention factor and taking the reference point, we can make these measurements where the least polar pigment has the highest retention factor. Column chromatography is used to separate compounds from a liquid or gas. So initially, the column is packed with a polar stationary phase, such as silica gel, and then the analyte is injected in the column, and then an eluent is injected to separate the sample. So this is a polar substance, such as water or ethanol, but less polar than the stationary phase. And different compounds are attracted to the eluent and get separated. So the eluent moves through the stationary phase, with the analyte molecules being attracted to it, and the most polar analyte, being the green one, travels the least distance as it's more attracted to the polar stationary phase, whereas the red analyte travels the furthest and exits the column first, and the eluted molecules are collected and analyzed using a composition technique. And that's a basic idea behind column chromatography. Distillation separates chemical species from a mixture by taking advantage of the known boiling point. And a typical example is a mixture of water, which has a boiling point of 100 degrees, and ethanol. So the mixture is placed in a distillation flask, and a thermometer is used to monitor the temperature, and you have a heat source or heating plate. So at 78.2 degrees, you get ethanol vapor being produced, and due to the molecules bumping into each other, you also get some water vapor, which is an impurity. Now the vapor passes through a condenser, which consists of a cold water inlet and outlet, where the water passes through the outer tube to cool the sample, and the vapor turns into a liquid, which is the distillate. So due to impurities, the distillation process needs to be repeated, and you can't achieve 100% purity due to the vapor pressure. So one cycle of distillation is known as simple distillation, and a similar technique known as fractional distillation is used to avoid repeating these cycles of simple distillation manually. Dye is dotted on a thin layer chromatography plate, and 3 pigments are observed to travel the following distances with respect to the position of the dye. And the solvent front travels 8 centimeters. Now assuming the stationary phase is more polar than a solvent, which pigment is the most polar? Well, the most polar pigment is the red pigment, because that travels the least distance because it's most attracted to the stationary phase. Now one of the pigments are placed on another TLC plate and the experiment's repeated, and the pigment travels 2 centimeters and the solvent travels 5.33 centimeters, which is the likely pigment that was dotted. So here you can calculate the retention factors for each pigment by dividing the distance traveled by the pigment on the distance traveled by the solvent front. And you can compare that with the retention factor from the second experiment. Now if the experiment is repeated using paper chromatography with a polar solvent, rank the retention factors of the pigments from the lowest to highest polarity. Well, in this case, the red pigment will travel the furthest. Substances with similar intermolecular interactions tend to be soluble in one another, and a solute is a substance we have the least of that dissolves in the solvent. So a typical example is sodium chloride, which is an ionic compound, dissolves in water. And generally polar solutes dissolve in polar solvents, and non-polar solutes dissolve in non-polar solvents. Now sodium chloride has strong electrostatic forces between the ions, and when it's placed in water, the ion-dipole interactions become more significant, where the oppositely charged dipoles surround the ions. And basically the ions dissociate in water. And this is true for other ionic compounds. Now pentane is an example of a nonpolar solute that will not dissolve in water. So the London dispersion forces between pentane molecules are more significant than the dipole-induced dipoles between a H2O and a pentane molecule. And large molecules like biomolecules are more difficult to dissolve. Spectroscopy separates the wavelengths of light, and differences in absorption or emission of photons in different regions of the electromagnetic spectrum are related to different types of molecular motion or electronic transition. Now microwave radiation is associated with transitions in molecular rotational levels. So when a photon interacts with a molecule, the molecule rotates. Now infrared radiation is associated with transitions in molecular vibrational levels. So for example, if this H2O molecule absorbs a photon, then it vibrates based on its molecular geometry until the photon is emitted. And with the CO2 molecule, which has linear geometry, the oxygen atoms oscillate back and forth. Now when a molecule absorbs a photon in the visible light spectrum, then the molecule gains energy and becomes brighter, and it loses energy when the photon is emitted. And similarly, in the UV light spectrum, the molecules gain energy, and in addition, bonds may get broken because the electrons can be ejected. When a photon carrying the right amount of energy is absorbed by an atom or molecule, then the energy of the species is increased. So we can visualize this using an atom where the electron jumps an energy level. And when the photon is emitted, the electron jumps back down and energy is released. So in the case of a lithium bar, for example, so as we saw using photoelectron spectroscopy, in that case the electrons were delocalized and the surface electrons are ejected when they absorb a photon. And this is the photoelectric effect. Now the wavelength of an electromagnetic wave is related to the frequency using the speed of light. In using Planck's constant, we can relate the energy of the photon to the frequency of the electromagnetic wave, with the units of frequency is hertz or 1 second. Now we can write the frequency in terms of the wavelength and then substitute into the energy equation, and you can then write the energy of the photon in terms of the wavelength. Spectrophotometry is used to measure the concentration of a solution over time by measuring the amount of light absorbed by the solution at different wavelengths. So here you have a light source, which produces different wavelengths of light, and you have a monochromator, which diffracts light into different wavelengths. And the light beam passes through an adjustable aperture, and then hits the sample, which is held in a cuvette or tube-like container. Now fractions of the incident wavelengths of light are transmitted and reflected from the sample, and a photodetector compares the relative intensity of two beams of light. So you run the experiment once to get a reference sample for comparison. And the current from the photodetector is converted into a digital number using an electric circuit, and the absorbance is displayed on the screen. Now the transmission is the light intensity of the current sample on the light intensity of the reference sample, and the absorbance can be related to the transmission using the logarithm. Now if the spectrometer produces specific wavelengths of light, then it's called a colorimeter. The Beer-Lambert law is used to relate the absorption of light, or absorbance of a solution, to the molar absorptivity, which describes how intensely a sample of molecules or ions absorbs light at a specific wavelength. And the path length B, or the length that the light beam has to travel through the sample, can be obtained from a spectrophotometry experiment. And C is the concentration of the solute or absorbing molecules or ions. Now the path length and the concentration are proportional to the number of absorbing species, but in most experiments, B and C are held constant. So therefore in these cases, the absorbance is proportional to the concentration. Now the Beer-Lambert law is most effective with solutions that visibly change color during the course of the reaction, but if the spectrometer emits UV light, then the Beer-Lambert law can be used to find the concentration of reactants in a solution that are invisible to the human eye. A 0.02 molar solution of an unknown substance A is used to create the following solutions. Now a spectrophotometer is calibrated at 400 nanometers, and the solutions are placed in a cuvette, and the absorbance values are obtained. Determine the concentration of substance A in each sample. Well, the first sample fully comprises of substance A, so it has the original concentration. And therefore, the molar concentration is equal to the number of moles of substance A over the volume of the substance in liters. And then from the number of moles, we can obtain a molarity of sample 2. And repeating this process gives the molarity of the remaining samples. Now what's the molar absorptivity of the substance? Using the Beer-Lambert law and any row in this table, which gives the following molar absorptivity. And plot the absorbance versus concentration and find the absorbance at 0.018 molar. So we draw a line of best fit and read off the absorbance. And you can compare this with the calculation using the Beer-Lambert law with the molar absorptivity from part B.